All right, let's break down the essential networking concepts that every single software engineer really needs to know. But instead of just giving you a dry list of definitions, we're going to do something a little different. We're going to follow the journey of a startup as it grows, and we'll see how each of these networking ideas pops up to solve a very real problem right when it's needed the most. So let's introduce our hero for this story, TravelBody. It's a brand new travel booking startup, and like most new companies, it's starting simple. Its entire application, the whole thing, is running on just one server. Sounds nice and easy, right? Well, that simplicity immediately creates our first big question. I mean, think about it. With millions and millions of devices connected to the internet, how does a request from someone's laptop in London find this one specific server sitting in a data center somewhere in Virginia? It's kind of like trying to find one particular person in a giant city with no street names or addresses. And the answer to that puzzle? It's the IP address. Every single device that connects to a network gets one of these, and it's just like a mailing address for your house. It's a totally unique identifier that tells data exactly where to go. So our TravelBody server gets its own public IP address. And just like that, anyone can send a request right to it. Problem solved. Well, almost. Yeah, let's be real. Nobody is going to memorize a random string of numbers just to visit their favorite website. It's not practical, and it's definitely not user-friendly. And this little problem brings us to the next critical layer in our networking stack. And that layer is DNS, which stands for the Domain Name System. The easiest way to think about it is like the Contacts app on your phone. You don't memorize your mom's actual phone number, right? You just tap on Mom. Well, DNS does the exact same thing for the internet. You type in an easy name like travelbody.com, and DNS works behind the scenes to look up the real IP address, that 203.0.113.10 number, and connects you, all automatically. Okay, awesome. So now customers can easily find our server using a nice, friendly domain name. But the second their request arrives at that IP address, we hit a brand new problem. You see, our single server is actually running a few different applications. There's the website, a database, and a payment service. How does this server know if an incoming request is trying to view a web page or if it's trying to process a credit card payment? The answer is ports. You see, a server has, get this, over 65,000 of them. And you can think of each port as a separate numbered door for a different application. So each service, the website, the database, the payment system, is listing on its own unique port number. That way, the server knows exactly where to direct every single incoming request. And this analogy just illustrates the relationship perfectly. The IP address is like the street address of a huge apartment building. It gets you to the right location. But the port number? That's the specific apartment number you need to find the right person, or in our case, the right application that you're looking for inside. All right, so things are going great for TravelBody. It's a hit, traffic is way up, but with that success comes a massive, massive security risk. Right now, we have our public-facing website, our super sensitive customer database, and all that critical payment info all living together in the same apartment building. If a hacker finds a way to break in through just one window, they've basically got the keys to the entire kingdom. So we absolutely have to separate these things. The solution for this is called network segmentation. What we do is we divide our network into smaller, totally isolated sectors called subnets. It's a lot like how a hospital has a completely separate secure ward for surgery and another one for maternity. We're going to put our public web servers in one subnet and our secure database servers in a completely different one. Now, just because we have these separate rooms, or subnets, doesn't mean the doors are locked. We need to control who and what can move between them. And that is the exact job of a firewall. It acts like a security guard standing at the door of each subnet. It inspects every single piece of traffic trying to get in or out and only lets it pass if it matches a very specific set of rules that we define. Okay, so our security is way better now. Our database servers are all tucked away safely in a private subnet, totally invisible to the public internet. But, whoops, we've just created a brand new problem. These servers are now so isolated, they can't get out to the internet to download essential things like security patches or software updates. They're actually too secure. The solution here is actually pretty elegant. It's called NAT, which stands for Network Address Translation. The best way to picture it is to think of a receptionist in a big office. Our private servers are like employees with internal-only phone extensions. You can't call them from the outside world. But when an employee needs to make an outside call, the receptionist places it for them, using the company's single public phone number. NAT does exactly that for our servers. So TravelBody is growing up, And it's time for the next big step in its journey. At this point, managing all this physical hardware is becoming a huge bottleneck. It's expensive, it's slow to scale up or down, and it's a major distraction. So the company makes the big move to the cloud. And the key thing to realize here is that even though the tools are changing, the core networking concepts, subnets, firewalls, NAT, they all still apply. They're just offered as managed services now. So now that we're in the cloud, TravelBody's architecture gets even more complex. They move to a microservices architecture. And while this is great for scaling, it creates a whole new headache. Developers start running into that dreaded classic problem, well, it works on my machine. Making sure every single one of those little services runs exactly the same way in development, testing, and production becomes a major challenge. And the answer to that nightmare? Containers. Using a technology like Docker, we can package up each microservice, its code, all its libraries, all its settings, into a single, neat, portable unit. The food truck analogy here is just perfect. A food truck has its own kitchen, its own power, everything it needs is built right in. You can park it anywhere and start serving. A container works the exact same way. It'll run identically on a developer's laptop or on a massive production server. But you know how this story goes. TravelBody's success just keeps going. And now we're not talking about a few containers. We're talking hundreds, maybe even thousands of them, spread across a whole bunch of servers. Trying to manage all of that by hand is just impossible. I mean, what happens when a container crashes? How do you scale up when traffic spikes? And how do all these containers, which are constantly starting, stopping, and moving around, even find and talk to each other? And this is where our next hero, Kubernetes, enters the picture. Kubernetes is what's known as a container orchestrator. It's like having an automated, super smart building manager for all of our containers. It finds them a place to run, it watches them to make sure they're healthy, it replaces them instantly if they crash, and it handles all of that complex networking between them, all automatically. Now, to really get how Kubernetes handles networking, you have to understand this one central problem. In Kubernetes, containers run inside these things called pods. And the key thing about pods is that they are temporary by design. They can be destroyed and recreated at any moment, and every time they come back, they get a brand new IP address. So how can other parts of your application reliably connect to something whose address is constantly changing? The brilliant solution is something called a Kubernetes service. A service gives you a single, stable IP address and a DNS name that never, ever changes. It just sits in front of a group of those constantly changing pods. So our other applications connect to that permanent service, and the service is smart enough to route the traffic to whichever pod is healthy and available at that exact moment. It's like having one permanent phone number for the sales department, even though the actual salesperson who answers the phone might change from day to day. So let's just pause and look back for a second. After this whole wild ride, from a single physical server all the way to a complex cloud-native cluster, it really all boils down to just 5 foundational concepts. You've got identification with IP addresses and DNS, you've got demultiplexing with ports, you've got segmentation using subnets, security with firewalls, and translation using NAM. That's it. And this, right here, is the most important thing to take away from all of this. The tools will always, always change. We went from physical routers to cloud VPCs to Kubernetes. But the underlying principles, the fundamental ideas of how networks function, have stayed exactly the same. Mastering these fundamentals is what truly matters. And that really just leaves us with one final thought to chew on. As technology keeps evolving at this breakneck pace, and the tools we're all using today are inevitably replaced by something new and shiny tomorrow, do you think these 5 core principles of networking will ever truly become obsolete? It's something worth thinking about.